Okay, welcome to a new segment. It's about counting. This is the last segment of the material in this class. So it's all about the glorified name for this is combinatoric, and the most exact way that you will use it is probability. It's counting, what's the probability of certain events in a computer system, but not. It's also actually counting objects. It's counting like possible ways that the data structure can values that some data can attain is also very important. Okay, so let's say that you want to count sequences of length 3 whose first element is a sandwich, so it's in the set. The second element is a side dish, and the third element is a drink, so it's in the set. So there's 3 possibilities for first element, 2 for the second, 4 for the last. Okay. So the number of way to count this is just it's the number of it's the cardinality of the first set times the cardinality of the second times cardinality of the third. Right? It's in a way the special when we talked about sequences and said, okay, you have a sequence of a certain alphabet, so every element in your sequence is a member of the same alphabet. So for example, binary, which is this, right? Fries 0, fruit 1. So then we know, okay, how many bit strings do you have of length 3? It's 2 times 2 times 2. It's 2 to the third power, right? But this is a generalization of this. If at a given index, the element is in one alphabet, and at a different index, it's in a different alphabet, and the different index is yet another alphabet, then okay, we just multiply these alphabet sizes rather than take a single alphabet from which, to which all of these elements would belong in the case of a sequence made of characters from the same alphabet to the third power. So this is the general rule, right? That the cardinality of a Cartesian product is just a multiplication of cardinalities of the set. And this Cartesian product is the set of sequences like this, where a j element is in capital AJ alphabet. And when I say alphabet, I mean set, right? So it's just natural for string to say string is a string over some alphabet, meaning every character in a string is a member of a given alphabet. This alphabet is a set, right? So in a binary string, the alphabet is bits. In a decimal string, alphabet is decimal digits, etc. So you can, the product rule, which says this, okay, is basically tells you, okay, if the process of making a string involves, first of all, I have to choose a 1, and I can choose this arbitrarily as a member of this capital A1 set. Once I'm done, I can choose a 2. So this is basically, you have, how many choices do you have when you make the first decision? This many choices. And then once you made it, whatever decision you made, the next number of, you will have this many choices to make this string, to pick this character, and these choices will be independent of what choice you've made here. Because in the example of dish ordering, right, it's like I was free to choose any side, regardless of how I chose my sandwich. and I will choose drink regardless of how I chose the sandwich and how I chose the side. So this can be seen as a decision tree. On top, you have A1 choices of choosing the A1 string, and then for each node of the tree, you have branches, this many branches coming from every node. So it's not a binary tree, it's a tree that has this many branches on the first level, this many on the next, etc. And it is important, this only works in the processes where the next set of choices is independent of the choices that you made so far. Okay, so say a school has 5 classes and you need to pick a student council. So there is one kid from every class. Okay, so let's CI be the set of kids in class I. So what's the number of selections for the student council? Is C1 cardinality to pick the kid from grade 1, C2 cardinality to pick the kid from grade 2, etc. And you have to make all these choices, and they're independent. So the answer is a product rule like this, right? So each student council selection is a sequence, and the sequence is of exactly 5 elements, and the first one must be in this set, second must be in this set, etc. Right? And the cardinality of this set is exactly this expression. So okay, so you have a triathlon. An athlete is doing a triathlon, and she has 3 choices every day. Okay, and they're independent. So she could have a schedule where she just runs every 7 days, or she could have a schedule where she alternate between them. How many choices there are? Well, that's the case of where each of the choices. So a choice is the sequence of 7 choices. Each choice is C1, C2, C3, C4, C5, C6, C7, right? Each of them is a member of this alphabet, and now it's actually the same alphabet. So it's the cardinality of this alphabet to the 7th, 3 to the 7th. The number of these schedules is exactly the number of 7-digit strings base 3. This is 0, this is 1, this is 2, right? So it's a one-to-one relation. You can encode this athlete's schedule as a 7-digit base 3 number. And there is this many of them. Okay. Okay, a chef for a school makes lunch menus for a month. So there's 20 days and 30 meals. And let's say that, we consider like a crazy cook who just makes the same meal every day. Okay, so that's still okay, in our way of counting, right? So I'm looking at the chat in case somebody pipes in. So the schedule has 20 elements, and each of the elements is chosen from the alphabet of 30 symbols, right? 30 different symbols for 30 different meals. And so it is a D. It's 30 multiplied by itself 20 times, right? So it's as if it was a 20-digit string in an alphabet that has 30 characters. So this is correct, indeed. Great. Okay. So okay. So this relates, as I said, to counting strings, right? Because if you have length n string over alphabet sigma, then the number of strings is well, this is the set of strings of n character strings over alphabet sigma, and the cardinality of this is that. Okay, so how many bit strings of length 4? 2 to the 4, right? Where the cardinality of the alphabet is 2, and the number of characters is 4 in this case. Okay, let's contrast it with a sum rule. So let's say that your experiment, okay, what you're counting out there can be described not as a sequence of independent choices in n sets, but rather it's a single choice. And the choice is, do I take something from set A1? Or do I take something from set A2 or from A3? So rather than do something in A1 and something in A2 and something in A3, you have to decide only one from, but you have a choice of any of these sets, but you have to take one element only. Now, if these sets are disjoint, so they have no common intersections, then, well, this is basically like choosing something from a union of these sets. So you're choosing something from this union, and how many choices you have? Well, that is the fact that you're choosing from the union is independent of whether they are disjoint or not. What is dependent, however, is that how many choices you have. So what's the cardinality of this union? And if they're disjoint, then this cardinality is the sum of the individual cardinalities. This is not true if they had intersections, right? In the extreme example, if A1 and A2 are actually the same set, then clearly the union of A1 and A2 is not the sum of cardinality of A1 and cardinality of A2. It's actually just one of them because they are the same sets. So A1 union A2 is the same as A1, and it's also the same as A2. So let's say that you have now modified menu where you choose a sandwich side and a drink, but a drink can be from either hot drinks or cold drinks. Well, but thankfully the intersection is empty, so the set of drinks is just the sum. I mean, it is always a union, but it's easy to count. The union cardinality is just 3 and 2, okay, by the sum rule, right? So now, the modified selection just makes the set of drinks larger. It used to be 3 on the previous slide because it was only hot drinks. You added 2 more, right? So simple enough. Okay, let's do this counting passwords, right? So this is an examples that are close to what I do. Okay, so typically, you go out there and you try they force you to choose a password, and you're like, okay, I have some password I like. You type it, and they say, no, sorry, it has to have a capital letter, it has to have a digit, it has to have this. Why do they do this? Because then the entropy of passwords you're choosing is larger. The space of passwords that you're choosing gets larger. So let's see how to count these. So let's say that the password is a string of letters or digits of length 7. So it's a string of letters or digits. Okay, sorry, I pronounced it as if it was either a string of 7 letters or a string of 7 digits. No, that's not what I mean here. I mean is that it can be every digit, every character can be either a letter or a digit. So it's a combination of product and sum rule. You make 7 choices, but each choice is now either from the green or the blue set, but they are disjoint. So you are making essentially a choice over an extended alphabet, which is a union of digits and letters. So that union has letters is 26, digits is 10, that union has 36 elements. So you're just making now 7-digit password over the extended alphabet. Okay, the alphabet that has 36 characters in it. What if you said that I want, okay, it can be a string of letters or digits, but it has to start with a letter. Okay, so what is the choice process now? Okay, a start character is treated separately, and for the remaining 6, well, they are arbitrary. So it's going to be like this, but just with 6 length, right? And what about this first character? Has to be a letter, so it's from a reduced alphabet. It's only from letters, right? So the first choice is from letters. So the next 6 choices are from the extended alphabet. So it's 26 for the first choice, 36 to the 6th for the 6th long string over this combined alphabet. Okay, so let's say that it's a string over this alphabet, but it can have either length 6 or 7 or 8. Okay, so let's make it the choice like this. The top choice is, are you doing a 7 character or 7 or 6 or 8? So you have 3 choices. I mean, you have the single choice and then 3 possibilities for it, for the answer. You know how to count each of them once you make that decision. And they will be all distinct, because a 6-character password is never the same as a 7-character password, and is never the same as an 8-character password. So these sets are distinct. So the top level decision is like a sum rule. You choose whether to take your password from here, or from here, or from here. In other words, either from here, or from here, or from here. It's a union, the total space of passwords, the union of these, but these are thankfully distinct. These are sets of 6 tuples, and this is a set of 7 tuples, and they're just syntactically different objects. Okay, so we can therefore just add cardinalities of these, but that's the sum rule. And within that, we already know how to do, right? These are the product rule, and then individual choices are again a sum, because you either go for these or for else, right? Let's say you have 10-digit strings, bit strings, but the first and last bits are the same. The last bit is a copy of the first. Okay, this should not be hard, right? So how many choices do you have, really? Please type on the chat. Right, it's this many, because the last digit is not a choice, right? It's just to copy it from the first. So you have 9 digits that you can set free, and that's it. Okay, so it's 2 to the 9. It's really, these strings can be described, but just the first 9-digit string. The last one is deterministic based on the choices that you have already made. Okay. Here is a general rule that is not so conceptually simple to apply sometimes, but sometimes this is a complete win. Okay, it's very hard to count something without it, but once you see that you can bite the problem using bijection, then you certainly know how to do it. Okay, so the simple fact, if you remember from functions, was that if you had 2 sets and a bijection between them, namely a function that is one-to-one and onto, then the cardinality of these two sets must be identical. Okay, I mean, a bijection is a one-to-one correspondence that can be inverted. So to everybody in X, there is someone in Y, and vice versa. So they can be paired up. They are the same sets of the same size. And basically, the rule is okay. This is a completely simple observation, right? But the rule says if sometimes it might be hard to count elements of some set X. The way the set X looks, you don't quite see it, like how to count it effectively. But you might find a correspondence between this set and some other one. And the other one is easy to count. Of course, this is just a way to count the original set, right? Because if you make this one-to-one correspondence with something that is easy to count, then you effectively counted X. That's what the bijection rule says. So, but here is one example. Okay. So, what's the number of subsets of set X? Okay, set X has n elements. So we said, okay, this is 2 to the cardinality of X, right? That was the formula. Why exactly was that? Okay, that the number of subsets is 2 to the n. Okay, we can give a bijection, very nice and very useful bijection between subsets of this set and binary strings of length n. And you already know, okay, we've been now drumming this for a while, right? That how many binary strings of length n are there? 2 to the n. And because there is a bijection between subsets of n elements set and binary strings of length n, so you can basically conclude from that the number of subsets must be the same as binary strings, so it's 2 to the n. That bijection is useful in representing subsets. So it's not only nice to finally put things together, but it's also useful because it's a natural way to represent subsets. You can represent subsets as bit strings. What is this representation? For every subset, let the bit strings that represent it be such if the ith element of the set. So first of all, I have to order elements of sets. This is okay. We said sets are unordered, but okay, there is some difference between these elements, right? Let's encode them in binary and let's just have lexicographic relation between them. So take it from the smallest, whatever notion of ordering there is, to the largest. Order them. And now the subset can be represented like this. If the ith element is in the subset, then the ith bit of the representation is 1. And if the element is not in the subset, then the ith bit is 0. So yeah, take for example n7, and here is your set of 7 elements, right? Ordered lexicographically. So a representation of a subset A, B, F would be 1, 1 for the fact that A is in and B is in, then a string of zeros because C, D, and E are out, 1 for F being in, 0 for G being out, right? So you add G, okay, then you flip that bit from 0 to 1. You throw out B and you add C, you flip this bit to 0, and you flip this bit to 1, right? And you can see that this is a one-to-one correspondence because every bit string clearly encodes some substrate in this way, and every subset can be encoded by a bit string. So it's one-to-one. Okay. So that algorithm, recursive algorithm that we use to count substrings, to count all the to count all the subsets. That was a recursive algorithm that, if you remember, it took one element out and then recursively said, okay, let's call it self on the one less element. And what did it do to combine? It took all from this branch and then did another copy, where for every subset here, you added a subset that included this kicked out element. So the number of subsets of an element set was clearly, by this algorithm, twice the number of subsets of n-1. So every time you kick out element, you multiply. Every time you add an element to a set, you multiply the number of subsets by a factor of 2. Since you start from a 1, so how many subsets there are of an empty set? 1. And you multiply by a factor of 2 with adding every element, then clearly that's another proof that it's 2 to the n, right? But anyway, either proof argues the same, but I would venture this one is more direct. Okay. Questions on this? Like, where is the bijection? Why is this a bijection? Okay. Another example. Let's count all 6-bit strings, which are palindromes, which means that if you reverse them, if you look at them in the mirror, so take the first one, make the first, here's the first, here's the last. Let's reverse the order. Make the last the first, and the first the last, and so forth. And they would be identical. Okay, so in other words, the first element has to be the same as the last, the second must be the same as the second to the end, etc. How many strings are there like this? Well, here's a bijection between 3-bit string and palindromes of length 6. Take any 3-bit string, and a palindrome is that string x and the same string x, but in reverse. Right? So you have these 3 bits, you can start them anywhere, and then you concatenate the reverse of these 3 bits. That function definitely generates palindromes, right? It has to be a palindrome, right? Because by definition, the end is a reversal of the beginning, and they are the same size. Okay. Does it generate all palindromes? Yes, because every palindrome, the first 3 bits is some x, and then the rest must be an inverse of that. It must be a reverse of that. So it is a bijection, and so it's actually easy to count them, right? It's just a number of 3-bit strings, and you can basically don't think of this as a case of a bijection. You can think like this. Okay, how many choices I have if a string has to be palindrome? I choose the first 3 bits freely, and then that's it, because the remaining 3 bits are determined already. They are mirror images of the first 3 bits I chose. But this is really the same argument. What you implicitly did was precisely this bijection. You identified that the only choices is really here, and then afterwards my choices are determined by the choices I made already. So it's no difference really between these 2 ways to argue, right? But you can see it that it's a case of a bijection. So okay, so this simple example we had before, right? Like where if I wanted to think of this as a bijection, it is a the reason was that there is only 2 to the 9 strings in this set, is because there is like a hidden bijection between the 9-digit bit strings and these bit strings. I mean, it's hidden, it's not very hidden. Which of these bijections is it that takes a 9-digit string and produces a string here? So it's not adding 0, it is adding the first bit of X by adding a copy of the first bit. It's this one. Yeah, thank you. Right, it's this one. Right. Again, it was simple to see without saying that it's a case of a bijection, but you know, it's also there's a like you can see it as a case of a bijection. Another way that can simplify counting. It's a kind of a generalization of a bijection. You have a function that maps one type of objects to another type of objects. First one is hard to count. The second type of objects is easy to count. The function is not a bijection, but it is a regular function, k-regular, in the following sense. For every k elements in this set are mapped to exactly to the same element in the other. Okay. So here is an example. You say you have a slumber party with a bunch of kids and they're running around. It's impossible to count them, but they all took off their shoes, and you have the box, and you could count the shoes. And you can count the kids that way, right? You count the shoes and you divide it by 2, right? So that is a case of the k-to-1 of a 2-to-1 correspondence between shoes and kids. That it was some function that mapped all the shoes to the kids, and it mapped exactly 2 shoes to every kid. So let there be a function with a property that a pre-image for every value, so that will be a kid. So this is a function mapping shoes to kids in my example. So every element in the image set, so that's a kid, if you take the pre-image of this function for that kid, which is a set of shoes that are mapped to that kid, then it's a k-to-1 correspondence if for every element in the codomain, the size of the pre-image is exactly k. Okay, there's exactly 2 shoes for every kid, and you know that the case, right? And so then it's easy to count. The set of values must be exactly the set of domain elements divided by k, right? So that would be shoes divided by 2. And you can set it up either way, right? Because you know, it could be that like perhaps it's the codomain to count, and this helped you count x cardinality. So you can also see it as the case of the 2-to-1 function. So this, you know, we're gonna beat this horse of the S10. Okay, these are bit strings whose last and first bits are the same. Actually, I can see it as a case of that there is a 2-to-1 function that maps 10 bit strings to these guys. The 2-to-1 function is it's not adding but replacing this one. I take a 10-bit digit string and I just replace the last digit by the first. Okay, it's clearly 2-to-1, right? Because how many pre-images a string has? Well, itself, yes, because it is, or the flip the last bit, because this flip of the last bit would get you know, squashed by this operation, would just be forgotten, this last bit, right? So it's two strings that get mapped into one, and therefore the cardinality of the set must be 1/2 the cardinality of this one. So this is 2 to the 10 by 1/2 is 2 to the 9. Okay, it's a little roundabout, but you can also see this as a case of that. Okay, so we have a bunch of you know, counting rules. It's not worth going over this because we just did. So let's count new types of objects. Something we call r-permutation. So you're so let's say you're making a sequence of an alphabet who has like this alphabet. So how many is A, B, C, D, E, F, G, H, I? It has 9 digits. But rather than making 4 independent choices, okay, you require that if the first element you chose is taken to be let's say this one, G, then the second element can no longer be that one, and the third no longer can be equal to these two. So whereas I asked you, okay, what's a 4 digits? How many 4-digit strings that are over this alphabet? Each choice of the digit was independent. If I ask you what's the r-permutation, which is a sequence of r items with no repetitions, then the choice of the first element influences the number of choices you have for the second. It's 1 less choice. And then next choice, you will have 2 less choices, etc. Okay, and these are just like, because they're strings, so these are sequences or strings, the order matters. So this sequence and this one, even though they contain the same elements, they're different sequences, you know, just like 2 bit strings that contain, you know, they have the same number of zeros and same number of ones, there are 2 different bit strings. So order matters. And now this question is, how many ways are there to select such, we call it r-permutation out of the n element set or alphabet. So the number of the selections is this. You have n choices for the first element, n-1 for the second, and so forth, right? So the last, since you're making r choices and the number of choices decreases, the number of possibilities decreases at every choice, the last one is n-r+1. And this can be computed as, look, this is the same as n factorial divided by n-r factorial, right? Because if I put this on this side, then these are the next elements, and by the time I multiply by n, I will have n factorial. And there is a special symbol for this. It's permutations out of n, I take r. Okay, it's a special symbol that we use. So say you have 4 tasks that needs to be distributed into 20 computers. And you have no restrictions on a number of tasks assigned to 1 computer. But there is only 4 tasks. So let's think whether, you know, what's the alphabet and what's the string? How long of a string and how to represent this choice? Well, okay. I maybe make it too hard. It sounded too hard. You have 20 computers out there, and the assignment of tasks, right? It's a sequence of 4, where each task can be represented by one of these 20 choices, right? So it's 20 times 20 times 20 times 20. Yes, because you represent this as a sequence of 4. The first element encodes which computer performs the first task. The second element encodes which computer makes the second task. The third, which of these computers makes the third task, etc. Okay, but so it's the tasks are independent, right? It's the same as 4-digit strings in alphabet with 20 elements. Oh, sorry. So, oh, this is really bad. I'm sorry, I overlooked it. This says how many ways are there to assign to the task to computers if each computer gets at most 1 task. So now I don't have this restriction. Okay, it can be. Sorry. Now I add the restriction. I don't want 2 computers to. I don't want the same computer to run this 2 tasks. So if I choose one of these computers for the first task, I no longer can choose it for the second. So it's a case of r-permutations. My alphabet decreases with every choice. If a computer was chosen to do the first task, then the number of computers from which I choose the remaining task is restricted. So that's an r-permutation for the case of R4 out of a set of 20. In other words, I choose a subset of 4 among the choice of 20, and I order them. So it's not just the subset, I order them because it's important which of these 4 computers I chose does the first task, which one does the second, which one does the third, which one does the fourth. So I choose them and I order them. Or I choose them in an ordered fashion in this way. These are equivalent, right? So I denoted as P24, but that's 20 factorial over 16 factorial. And in other words, this is a number of 4-digit strings in this alphabet which have no repetition. So whatever digit encodes a given computer cannot occur more than once. So it's a number of 4 permutations of a 20-element set. Okay, you have 30 prizes and 3 kids who select these prizes from a bin. How many choices there are, right? So you first say Larry goes first, right? And they pick. So there's 30 choices, but then Curly has a reduced set, it's 29, right? It's a 3 permutation of a 30-element set, right? So it's a sequence of 3 characters in a 30-character alphabet that have no repetitions. So yeah, so it's as the student says, it's 30 times 29 times 28. So now let's say 3 prizes in a class of 100 students. Let's say that there's no restrictions on the number of prizes a single student can get. So the student can get all 3 prizes can fall on the same student. Okay, then how many choices? Yes, it's 100 to the third, exactly, because it's a 3-element sequence of 100 choices for each character, right? And now let's say you put this restriction, but no student gets the same price. So it's now a restricted, the alphabet is going to decrease with every choice. It's the 3 permutation out of 100 element set. Okay. So this R permutation is related to a notion of permutation, right? So permutation is a sequence that contains elements of a finite set, but exactly once. R permutation is a permutation over some set is an n permutation, where n is number of elements in the set. So permutations of a 3-element set, there's 6 possibilities. And what's the general formula for R permutations, right? It's n factorial over n minus r factorial. In this case, r is n, so n minus r becomes a 0. So that vanishes. 0 factorial is a 1, so it's just n factorial. So if you have a 5-element set, it's 5 factorial, right? How many way of orderings are there if you I'm sorry, like the fonts are completely messed up. I mean the sizes, right? Like there's something happened. I don't understand, but I have to fix that. Anyway, it's readable but ugly. How many permutations where I say that B and E must be next to each other? So let me give you a hint. Like, let's make B and E one letter. Yes, so somebody says 2 times 4 factorial, 2 times 4 factorial. Why is that it? Because we either make BE one letter or we make EB one letter. Now, permutations over this set and permutations over this set are disjoint, right? And one of them BE occurs and the other EB. So we can count them separately, and it's just 4 factorial each. So this is an answer. What if I said that B must occur immediately before E? Okay, so that's even simpler, right? Like it's just B, it's a single letter, right? This is easy to confuse when you say these 2 choices, right? B are next to each other is a choice between either BE or EB. B immediately before E there is no choice. It's just that BE becomes a single letter. You can see where I'm going. What if I erase the immediately? Okay, so I want to have permutations in which B is somewhere before E, but not necessarily before, not necessarily immediately before, right? So I just want that, okay, I have to permute these letters. They all must occur. And I want to count only those permutations in which B comes before E. I know they must occur both, right? So B and E must be somewhere in the permutation. But I want to only take the ones. I'll give you a hint. This is a good case of either 1 to the bijection or 2 to 1 way of thinking, because think about all permutations and think that there is only 2 possibilities of arbitrary permutations. You can either have permutations where B occurs before E, or permutations where E occurs before B. In other words, B comes after E. So you either first encounter B and E then, or you first encounter E and then B. This seems to be like a partition, right? Permutations have to be either in the B first class or in the E first class. Could you use this fact to, and you know that the total number of permutations is 5 factorial. Can you now say what is the size of the permutation? How many permutations are in the B first class? And to answer this, just think of the only bit that you need to know is the following. What do you think about the size of the B first class relative to the size of the E first class of permutation? What would be your guess? How many B classes there are, B first permutations there are relative to E first permutation? Yes, and the student writes correctly. So if you were to say, like, so what is the conclusion? Like, what is the relation between B first permutations, the number of B first permutations, and the number of E first permutations? Is there any reason to think that they would be different? You're just taking two letters and saying, I want B before E. Or you take a different set of letters, E and B, and saying, I want E before B. You just arbitrarily chose two letters and you asked that one is before the other. There is no difference between these 5 letters, right? And as far as you count permutations. So whichever two letters you choose, and you say, I want them to be in this relation, like the number of such permutations should be independent of whether you chose A and C to have such a relation, or E and D, or B and E, or E and B, right? This making such an imposition should reduce the set of permutations in the exact same way. So the B first and E first, they are the same sized. The set of B first permutations and the set of E first permutations have the same size. Why? Because there is a bijection between them. The bijection is oh, okay, I don't have the bijection here. Okay, you know what? So let me first tell you the bijection. What is the bijection between B first and E first? You tell me. Take the B first permutation and convert it to a E first. What would this conversion consist of? I guess the lousy interface, so maybe someone is typing. Switch the position of E and B. Exactly. Thank you. Right, that's the conversion. Just take your B and E and you flip them. Flip their positions, switch their positions, right? That is it's a permutation. It's a one-to-one function between B permutations and E permutations. You clearly went from B permutation to an E permutation. Do you get all of them? Yes, because you preserve the order of everybody else, right? So these two sets have to have the same cardinality, and they have to sum up to 5 factorial. So each of these sets have to have cardinality 5 factorial divided by 2. The explanation here I have is actually casting it as a 2-to-1 rule. It's here I explained it as I take all permutations and I do this, I take out only the B first ones, okay? And what is the 2-to-1 function that maps any permutation to that one? It's a function that looks at the permutation identifies B and E, and if they are in the correct way, it leaves, and if E is first, then it flips them. That's a function. It took an arbitrary permutation, and it spat out a B first type of permutation, right? And it's a 2-to-1 function because there is two ways to get to any permutation. It's the same permutation, gets mapped without changes, and also the permutation where B and E were switched. That also got mapped to that permutation in the B first set. So it's a 2-to-1 function, and it's sort of directly. It's even Stephen. Like maybe you can think of the equality of the two sets. Yeah, and then you know they have to sum to factorial, so they have to be 5 factorial over 2. Or you look at it as a 2-to-1 rule, right? They lead you to the same conclusion. Okay, I think that's a good place to stop, right? Like, so yeah, the subsets are, it's r-permutation, but now I think of it as a set. So I stop caring about the order of this, and it's a different beast. Okay, let me